Hello, everyone, and welcome to our new webinar series, Open Cosmos Conversations. My name is Marita Georganta, Ground Segment Team Lead of Open Cosmos, and I'll be your host for today's session. I am joined by David Rijlaarsdam, Director of Space System Engineering at Ubotica, and Javier García Robles, Data Partnerships Manager at Open Cosmos. David, thank you so much for joining us. To kick things off, could you introduce yourself and tell the audience a little bit about what you do?
Absolutely, it's a pleasure to be here. So I'm David Rijlaarsdam, as you said, Director of Space System Engineering for Ubotica. I am responsible for the company for the space operations and our space systems. As such, I've been involved in almost all our space missions, including a lot of our joint missions with Open Cosmos, including Hammer, Cognizant 6, and Accenture 1, which of course we're currently working on. My background is in space systems engineering, and I've been with the European Space Agency and Intel Movidius before Ubotica.
Pretty exciting stuff. Thank you so much, David. And Javier, can I pass it on to you? Can you give us a quick introduction as well?
Yeah. Hello, everybody, and thank you for inviting me to the webinar. So my name is Javier García Robles. I am the Data Partnership Manager in Open Cosmos. I'm leading all the interactions that are done with analytical companies that produce insights from our images. And my background is I'm a telecommunication engineer, specialized in Earth observation and remote sensing. Previously, I've been working quite a lot in radar interferometry, and now opening this new chapter since 2 years ago in Open Cosmos.
Thank you, Javier. Perfect. So today we're diving into one of the most exciting advancements in the space sector, which is the shift towards in-orbit intelligence. For years, Earth observation relied on a traditional model where the satellites captured massive amounts of raw data, held onto it, and waited to downlink it to the ground stations for further analysis. But today, we're exploring how advanced onboard AI hardware and smart satellite networks are changing the game by processing data directly in orbit via satellite edge computing. This delivers near real-time insights when they matter the most, whether that's for tracking active wildfire fronts, optimizing climate resilience, or improving maritime domain awareness. And today, I'm going to be discussing with you, David and Javier, and I have some questions for you that I would like to open up. Why do we use Earth observation and AI together to address the unique monitoring challenges of the maritime domain?
Okay, if you want, I can start. So the main challenge nowadays is the maritime domain is vast, and traditional Earth observation relies on a slow capture, hold, and downlink model, making it impossible to catch up moving illicit activities in time. So that's why we are combining right now Earth observation and AI to really capture that with onboard edge processing capabilities. So the satellite just not take the picture, but it extracts insights near real time and can download that very fast. So that does not depend purely on ground stations, but also it depends on telecommunication infrastructure to help receive the data within minutes on ground.
I think that's a great answer. The way I like to explain it is that Earth observation was never really designed to monitor dynamic events, so things that move or things that change fast, because we never could do that. All the satellites, Earth observation satellites, used to be model on, so it's just scanning the Earth and then downlinking the data whenever there's a ground station available, as you say. Which is great, but it's too slow to really monitor things that change fast or things that move. So indeed, you need Earth observation for the vast monitoring required for maritime security, and you need AI to make it fast enough to actually capture the dynamic events as soon as they happen.
Thank you both for your answers. And if we can just start diving in, I have a question. What are dark vessels?
So dark vessels are ships that intentionality turn off their automatic identification system, the AIS transponders, the mandatory tracking system used for navigation and safety. By going dark, they vanish, they go invisible. from standard commercial monitoring systems and then making them totally invisible for traditional maritime tracking. This is typical link, not necessarily not necessarily bounded, but can be linked to illegal activities as they become invisible.
Thank you, Javier, for your answer. What are the primary civil or commercial activities that they are trying to usually hide?
They can be different kind of activities, from illegal bunkering, smuggling, or even illegal fishing. Can be linked to environmental, or can be to exchange materials or avoid paying taxes within the country, so they go to international waters to do that. So it can be various things.
I think you name quite a few very relevant cases there. I think it's important to note that not all dark vessels are necessarily doing something illegal, right? There's various reasons for why a vessel is dark, but I think what's very clear is that stakeholders that try to establish maritime situational awareness need to know what's going on, no matter what the reason is that a vessel might be dark. And we talked before that about the different types of sensors you can use to do that, being terrestrial radar, for example, or simply observations from other ships in the area. However, none of that really scales over vast areas and over sufficient revisit to really get a near real-time picture. So there's many things that dark vessels could be doing. Some of them nefarious, others not nefarious. But in general, I think the point is that our stakeholders need to know what's going on in their maritime domain, and therefore we can't have dark vessels either on AIS or on other data sources. We need to know what is happening.
Okay, so here we can see an image, a satellite image in the natural true color image. We can see some vessels here, a port here. If we zoom in this area, we can see two ships that are all together. So this is an example, not necessarily linked to that, but it's an example of potential ship-to-ship transfer and how we can monitor that if those ships will go to dark, which maybe is not the case, but from Earth observation, we can see that in almost near real time.
Thank you so much, Javier, for showing this. And David, you have made some very good points earlier. And we do hear a lot about sea blindness over vast areas. How do we make sure that we're looking at the right areas at the right time, especially when it comes to critical infrastructure like subsea cables, pipelines, wind farms? What would you have to say about that?
Yeah, it's a really great question. I think historically Earth observation has tried to just monitor vast areas and then on ground see what data was useful. And like I said, for dynamic phenomena, that won't really work because you just don't have the capacity to monitor those areas that matter most at the time that matters most. So what we try to do at Ubotica is predict where value in Earth observation data will occur in the near future. And for maritime security, we do that by predicting risk. So we propagate out over the next period of time, let's say it's 10 days or so, where we think risky vessels will come, and we combine that with different data sources that tell us something about the inherent risk of the location. So to give you an example, our stakeholders don't really care if there is a risky vessel in an area where there's no critical infrastructure, for example, where there's nothing that could be damaged by, for example, either an accident or a purposeful act. However, obviously, if there is a ship that's coming close to an area where there is critical infrastructure, that means that inherently there is a higher risk of something happening there. Now, we have ways to predict that out from into the future from the data that we get in, and by predicting where risk will occur over the next couple of days, we can also then calculate where the most the highest quality and most data is needed, and when it is needed. So we can tell our satellites in advance where we think they should take imagery. And then we have AI running on ground to determine what is the most optimal satellite to take that image, because obviously not all satellites are everywhere when you need them. So we solve an optimization problem and tell our satellites where to look. If we then combine that with onboard AI, again, we get that information back very quickly, and we can update our risk models for the coming days. So that means that we try to predict where to point our sensors and when to turn them on. And that way, we make sure that we get the data that is needed in near real time. So we'd like to say that we know which data our stakeholders need before they even know that they'll need it.
And if I can ask one more question, David, on what you said, and Javier, I'll pass it on to you afterwards. You say that you do have risk models to predict where it would be. Do you start by studying where critical infrastructure exists and you work your way backwards then? Would that be how you do it?
Yeah, that's one of the data sources that we use. Absolutely. Yeah. So we know where there is critical infrastructure. And then there's all sorts of other data sources that we fuse with that. So, one of the elements of, for example, determining which satellite needs to take the acquisition is, of course, weather. Weather is like our optical satellites cannot see through clouds. So this is something we also take into account. We, in general, need to take into account weather because vessels sail faster if they have the wind in the right direction, for example. So it's another thing we need to take into account. We also need to take into account shipping routes. Not large ships can't go through shipping routes to locations on the sea where there is not sufficient depth for them to sail through, for example. So there's a very large range of data that we need to take into account to make those predictions. But yeah, the location and nature of infrastructure is a very important one.
Thank you so much, David, for the further information. And yes, Javier, if I can also give the stage back to you about critical infrastructure and how, when it comes to critical infrastructure, how do we make sure that we are looking at the right areas?
Okay, for critical infrastructure and in general, for all the kind of observation, I think EO, Earth observation, provides situational awareness, insights, information, almost like in 2 hours, you can receive the image to download, and you can have like a vast analytics on what's going on in that region, in that area. By processing on board, you can have like that in a very, very short time. Of course, you will not have the whole cube of data, but you will have like initial insights and in 2 times, like in the 5 minutes, you will have some relevant information that to activate or to do some kind of inform actions. While in certain amount of time, when you receive the data through the ground station, you have like the whole pile of information. Whilst also our satellites are providing also IoT, and they have telecommunication capacity, they have AIS. So IoT also can provide health checks on some of this infrastructure. For example, the wind turbines. Through sensors, they can determine if they are working properly or not, or if something's going on them. And they also this information can trigger or can activate Earth observation acquisition. So we can program the satellite if we detect something is not going on. And this is just a specific use case on maritime, but that can be propagated or can be done in other verticals. Such I'm going to put a very, very quick sample of fire detection. If we're detecting smoke or heat increase by IoT, these satellites can operate very fast through the sensors to acquire in the next pass over the area. And that's why also our next generation constellation, which is formed by satellites, all of them are having this AI edge computing framework. They are all having AIS, so they can provide also this near real-time and on real-time information about the ships, or they have Earth observation. So it's all mixed together, and we can combine that also with inter-satellite link to download this first quick analytics.
Thank you, Javier. Can I just ask you, you did mention about the different types of sensors that they are on board. Are you saying that maybe some of them are on collecting some data in real time and then trigger more sensors to turn on to acquire more data according to whether there is something going on the ground?
Yeah, that's a whole use case about determining whether there is a situation of risk or something that might trigger an observation from the satellite. And that can be definitely done through sensors that are connected to the network, to the internet, and then or directly to the satellites to put on the IoT from the telecommunication satellites or the Earth observation satellites, so they can program the next acquisition of the satellite.
Well, very interesting. Thank you so much, Javier. And if we have talked about different sources of data, different data, we have talked about the words fusing, and we generally talk about fusing Earth observation imagery and AIS data. How do Earth observations and AIS actually work together to expose activity that would otherwise go unseen? Maybe I can pass this over to David.
Absolutely. Yeah, it's a great question. So, we talked before about some vessels having AIS on and others not having AIS on. And so I think that's the first way you can combine these, that, if you take a satellite image and you use onboard AI to detect all the vessels in that image, that you can compare that to the AIS data source and say, this vessel right here doesn't have AIS on, so you can see which of the vessels is dark. The other way you can combine it is through the ships that do transmit AIS data. You can fuse that data with the ships that you are seeing in your satellite data. And you can do that on board using orbital AI, or you can do it on ground. And with that, you can identify uniquely the ships that you see. So, if we combine the two data sources, we can say what a particular vessel actually looks like in real data. And that is useful because after that, we can store that in our database and compare it again using orbital AI the next time we see a vessel. And we can compare it also on its spectral fingerprint. So we can, for example, say, this ship has this particular wavelength response due to the paint on its deck. And we can compare that through earlier entries in our database and say with a degree of confidence that it is a particular ship that otherwise would go unidentified.
Very interesting. Thank you so much, David. Javier, if you want to jump in with any comment, please feel free.
No, I think David just provided the whole information. The AI tells where the ship says it is and which kind of ship, nationality, and other relevant information. EO observation shows where a ship actually is at that moment. So the cross-reference, the fuse of both informations is where you can look at anomalies and do this intelligence behind what really you are seeing.
But so what is the flow of information after you have identified the dark vessel?
Yeah, I mean, it really depends, right? It depends on what the context is. So it depends on where we are in the world, if that's an outlier or not. There are locations in the world where there is vast areas where AIS is not used or not working. In other areas, it is really strange if a ship does not have AIS, and then it is something that our systems would throw an alert for, and would inform our stakeholders, and they can then make a decision on what to do with that information. If it could be causing a dangerous situation, then obviously it's something that perhaps the Coast Guard should be informed on, for example. But that in our flow we analyze the data, we provide the relevant information that the stakeholders need, and so the answer is a little bit that depends on the exact situation.
Hear you. Thank you, David. David, if I can ask you, can you walk us through the first phase of the continuous intelligence loop? How do your algorithms build and update the living risk map?
So that's a great question. So we start it's a continuous loop, but let's start at monitoring vast areas using AIS data, radar sources, satellite data. We take in all that information, and for us, obviously, what's a key differentiator is data based on orbital AI, so data that we collect and then process onboard spacecraft and then act upon. And I have an example of that I can show you. So where we might start is this, and this is raw data as it comes from our satellite, and this gives us IDs of vessels, in this case latitude, longitudes, lengths, headings, detected by artificial intelligence on board our spacecraft, and this gets sent down over intersatellite link. So in near real time, we get this down in a few minutes down to ground. Now, this is interesting, but you should obviously use more information to actually make this useful. So I'm going to show you something else. So if we plot this information on a map, now you can obviously see where this is. So this is around Carg Island. It's an older image, so this is something that we get in near real time, but something we would keep to ourselves because obviously it's a very sensitive area and we don't want to get anyone in trouble. So this is something that we're now comfortable talking about now that it's been out for a while. So what you can see here is those detections plotted on the map. So that means that now we know in near real time where there are which type of vessel, where they are sailing. And we can combine that with other information, for example, AIS, to say which vessel is which. Now, in this example, they're actually all dark, so we couldn't actually do that. But it does allow us to say something around an area where otherwise there is no or very little information available about the particular vessels. And then, of course, let's say 45 minutes later, this image comes down through our ground station, and we can cross-reference our detections with what we see in the actual imagery. And you can see that here. So our detections mostly match what we actually see in the image. So once we have that information down, we fuse it with these other data sources that we talked about, and that could be anything. That could be AIS, that could be radar data, that could be data from public sources, Morse code, etc. And that allows us to identify the ships, sometimes say something about where they're going, and fuse that into a situational awareness picture. Then that situational awareness picture we use as input into our risk prediction models. So we predict out what the risk profile of our areas of interest will be over the next period of time. And once we have that, we again schedule our satellites using our on-ground AI to say we are, and also our other sensors to say, we need these data points 3 days from now at that time because we predict that there will be a risk that arises here. And then the loop starts again, right? Because then we collect that data, we again analyze it, propagate our risk map out, schedule better sensor acquisitions, get a better risk map, etc. So our system really provides a feedback loop here. And that means that we get better data over time because we get better at predicting the risk, and because we get better data, again, the risk predictions become better. So this is a self-enforcing process.
And if I understand correctly, then over time you get better data, but that also gives you a very good idea of what's happening in real time, how the events evolve, no?
Yeah, absolutely. So, we have as always, a finite amount of resources, so we cannot point our satellites everywhere all the time. So indeed, the better we can determine where to make data takes, the better we can say what is happening in real time, in particular at the times and the locations where it matters most.
I see. Thank you. And once a specific anomaly is predicted on that map, how does that insight automatically trigger where the satellite constellation should look next?
So that insight will go into our risk models, and our risk models tell our satellites through on-ground systems, tell our satellites where to look next. So because we can say where risk will occur in the near future, we can point our satellites to where that risk is present.
And Javier, would you like to add something on that?
Yeah, that's important to mention also that the systems, the constellation that we are run, the open constellation, runs under interoperability of all the satellites. So once we can have like repetitive observations over the same area, or they can combine observations to cover a large area. And it's important because David mentioned before that they will need like more sources of observation, more satellites passing through to really obtain the evolution of the situations that they are observing. And that's where also Open Cosmos is increasing quite a lot, the capacity, or with the next generation of satellites, we will have sub-daily revisiting time. So that goes together with a combination not only of multi-sensor, but also on the combination of multi-times per day that we can observe a critical area that is overgoing to a situation that needs to be observed.
I hear you. And what this means, Javier, is that with more data, with more sources of data, and with more passes, then we get a clear picture of what's happening in real time, how the events evolve over time.
Exactly. That we will help on receiving this kind of service that they are needed for really for situation awareness of us. For example, an oil spill. How is it evolving? It's going towards south. It's going towards west. Who has caused the oil spill? For example, let me show an example. So here we have an image, the spectral image, and we are observing different ships, but also we are observing an oil spill detection over here. And if we move towards the north, we see also other smaller, what can be identified visually at the edge, like potential oil spills. But we also can see which are the ships surrounding this oil spill. So that's a very relevant information. But if you have this information, let's say every 2 hours, you can derive who has specifically caused that, or where these oil spills are heading, if they are under control, or there is like a situation that some vessels like are trying to to confine them. You can provide like relevant information, as well as information that here, for example, there is an oil spill that doesn't have any ship very close. So maybe it's a natural oil spill, but you can observe that over time. What are the situations, or who was the trigger, and of that situation. So there are evidences that can be obtained together with AIS, Earth observation, and multiple revisiting times of that. And let me provide another example. This is very link of what David has told, that not necessarily all these ships that are doing ship-to-ship transfer are doing smuggling activities, that can be happen. But here, you can identify this is all the vessels that over a certain area, and we can identify very quick. And also, Ubotica can do that all on board of the satellite with the analytics, thanks to our satellite infrastructure, which are the ships that are altogether ship-to-ship transfer, and which ones are isolated, like alone itself. So this is also a nice example, visual example of what can be obtained on the satellite, not the analytic, but also the image that can be downloaded afterwards.
So we have seen some of your use cases that they look very nice with images and boxes and vessels, but the satellites themselves do not actually take data like this. It is huge amounts of raw data, very difficult to read. How does the final deliverable to the user look like? How does it all come together?
Yeah, of course, it depends a little bit on what the user needs, but eventually we fuse the insights that we gather from our satellite data with all these other relevant data sources, and then we deliver a finished data product to the user. And we do that by either through an API, by integrating into their existing solutions, so we don't give another extra screen to an operating team that's already very busy. Or if necessary, we can provide an end-to-end integrated solution. So I guess the most important thing to say here is that we don't necessarily want our user to be concerned with raw satellite data or even process satellite data. We just want to present the most relevant information. And that might involve imagery, that might involve data takes if they require that, the underlying data from the information that we present, or it might be as simple as a map with current ship locations and their assessed identity.
Perfect, thank you. Javier, is there anything that you would like to add also?
Yeah, that satellites have it's a cube of data, so there are different bands, and in this case we are talking about hyper-400, that is hyperspectral, 5-meter resolution, 32 bands. One of them is panchromatic, but we have 31 bands more. So you have to imagine like a pile of bands, and the amount of information that can be obtained through this, not only about where a ship is, but also like there is an oil spill surrounding it, or what is the turbidity of the coast or on the sea. Let me show you an example. So this is an example of an hyper-500 image. We was just saying before that there were some examples of ship-to-ship detection, but we are also here observing some turbidity over the coast, some ships crossing here the Suez Channel. So we can observe like a vast amount of information. This is a false color image formed by band 13, band 15, and band A, like doing a false color image, but also highlighting in a different way this area where there is a lot of water flow from probably some agricultural areas. Yeah, and a single image can explain a lot of stories behind, and that's where we need to process this data in the right way and to highlight which are the analytics that the end user that is not expert on Earth observation need to obtain. We have to transform that and explain that in the right way, And the thing a little bit as what David was explaining, that how the end user is expecting the image on their side, not the raw data or the raw bands, but the identifications, the delineations, the polygons, and or weighted analytics, so they can take decisions on top of that.
That is very, very good. And that would be the end of my questions for today, for the two of you. I would like to leave 1 minute. I would like to leave the floor back to you, David and Javier, if you want to say any final remarks to the audience for today.
We are in the beginning, let's say, of a new era of satellites like microsats or small sats, let's say, and that are very agile. It can be launched to the space very in relatively short times, and they can be combined all together in constellations. So we are in the beginning of presenting some services that didn't exist like 5-10 years ago. And yeah, this is evolving very fast, and even it's fast for everybody, and also fast for the end users that are receiving this data, that have some capabilities that they even think about. So yeah, we are in this transformation times that everything evolves really fast, and it's quite exciting to be on that domain, no? And to serve and try to unblock, which will be the next step towards delivering very, very fast information that can help in general the humanity.
I think that's really great. I totally agree. It's a very exciting time. I think orbital AI is changing how Earth observation is used, and it's going to make it orders of magnitude more valuable for society. And I think the maritime security use case is one of the first use cases where we're already seeing that happening.
Exciting times. Perfect. Thank you so much, Javier and David, for sharing those insights with us today, and for sharing all of your thoughts. And to our audience, thank you for tuning in to the first episode of Open Cosmos Conversations. Make sure to keep an eye out for episode 2, where we will continue exploring the cutting edge of space data and global partnerships. Until next time, thank you for watching, and have a wonderful rest of your day.